Hi everyone, just confirm audible. Okay, let me know. Great. So I think audible, right? Okay, so today we are going to start a very important session, which is a complete tour on semaphores. Okay, so which means I will discuss everything about the semaphore. Whatever is needed, I will discuss here. Right? Okay, so let's get started. Cool. So now, let me just tell you that what we are going to discuss here. We are going to discuss reader-writer problem. We are going to discuss semaphore. We are going to discuss anything and everything that is required for the semaphore. Okay, so including all the classical problems also. So let's just review that what we have seen in the previous lectures, right? So if you remember that we have taken some marathons in the previous classes. So let me just tell you that what is the marathon that we have taken earlier. So we have taken the marathon regarding the like operating systems. In operating systems we have taken two marathons. So one of them was regarding the process synchronization, right? So let me just put the screenshot here, that which marathon I'm talking about, and then you will be probably able to relate more, right? Okay, so see this. If you just search on the YouTube the Go classes marathon, right? So there you will be able to see. So see this particular slide that we have already seen these marathons, right? So basically if you just search on the YouTube, then you will be able to see multiple marathons that we have taken last year and this year also. So we have already talked about system call and these things, right? So this was one of the marathon that we have taken, and then we have talked about the process synchronization. This was another marathon that we have taken. Okay, so the process synchronization marathon we have already taken, and now today we are going to talk about the semaphore. Okay, so let me just tell you that, see, the process synchronization, this particular marathon we have already taken. So just watch it, right? And now today we are going to see live. I mean this is the live. So we are going to see the marathon on the semaphores. So in the process synchronization, we have seen couple of the methods to synchronize. So can you tell me what are those methods? Hardware related methods, software related methods, and these things, right? Let me know if you have seen, if you have seen previous marathons. Okay, let me know if you have seen. How many of you have seen the previous marathon? How many of you? Okay, so if you have not seen, then I will just recommend that you can definitely see that previous marathon. If you just search on the YouTube, then you will be able to see that. Okay, and not only that, let me just tell you, for the operating systems, right? For the operating systems, we have basically, for the operating systems we have covered these many lectures. I mean, these many lectures we have covered earlier for the operating systems, which are, if you notice, related to system call, thread, and everything. Almost everything we have covered in the operating system in the last year. So you can definitely check out this playlist. This playlist has got many views. This is 18,000 views we have got on this playlist. So just check out this playlist, right? Okay, great. Yes, we are going to see classical problems here also, right? Yes, yes. Okay, great. So Ajit is saying that you have not replied on the Telegram. So Ajit, on the Telegram, it is really very hard to reply. So I'm sorry about it. So I mean, now generally we get many messages, and we need to take care of the classes, take care of the quizzes, take care of the many students. So you won't believe that it is really hard for us to manage all of the things. Like, we need to reply on the gate overflow, we need to reply on the Telegram. So that's why we tend to miss it. We are sorry about it. Okay. So we have seen the hardware related solution. These are fast, and but there are problem. Like, if you remember that there was a problem of starvation, right? In the hardware related solution, there was a problem of starvation, which was test and set. We have seen, right? Test and set. Okay, and we have also seen the software related problem, and those are slow. Generally software related problem are slow, and hardware related is fast, and software related is slow. But there are problems in both of them. For example, in hardware related, this is suffering from starvation. For software related solution, we have seen the Peterson solution, right? Peterson solution. So what are the problems with Peterson solution? The problems basically is that it is only for two process, right? And even if you want to extend this for multiple process, then you need to know the value of n in advance, which means let's suppose you want to extend it for 10 process, then there is an algorithm called Decker's algorithm, and there are other algorithms also, but for that value of n, that how many processes are going to be there, that n should be known in the advance. And also proving the difficult like proving that this particular solution is going to work correctly is also a very difficult part. So that's why see, we have process synchronization as a one big issue. Process synchronization, this is a one big issue, but here we have multiple solutions. One is that user based or software solution, right? User based or software solution. This is one thing. Another is hardware based. Another is OS based. Okay, OS based. Now today we are going to see OS based solution, which is also called as Semaphores, right? Semaphores. And what are the hardware based? This is, for example, test and set. What are the user based? It is, for example, Peterson's, right? Peterson. Okay. Yeah, thank you, Abdullah. So Abdullah is saying that, sir, you are a great teacher, really, because you always go in the depth. Thank you so much. Okay, great. So now let's get started with today's session, which is Semaphore, right? So this this particular slide I have taken from Galvin. This is I mean, for the Semaphore, I have taken this particular slide from the Galvin. So basically, if you have noticed that there are few people which are in the row. So they are saying that these people representing the waiting queue. Okay, so these ones to get executed, and then the bouncer represents the semaphore. Anyway, you will get to understand this meme later on. First, you understand the semaphore. By the way, this Semaphore was given by Digextra. You might have heard about Digextra, right? How many of you know about Digextra? How many of you already know about Digextra? Tell me. You must be knowing, right? Okay, great. So Dijkstra is basically I mean, he's obviously very popular for his shortest path problem, but not just that. He has a great contribution in computer science, not just the shortest path problem. Okay, great. Now let's just get started with the semaphore quickly. Okay. So the semaphore is basically can be accessed using two automatic operations, which we call P and V. Okay, P and V. So it can be accessed only using two atomic operation. So think about the semaphore as a value number of empty chairs as a table in a table. So what do I mean by that? Let me just explain. See, semaphore is just you just treat you understand the integer variable, right? Integer int a. You just treat the semaphore just like an integer variable for now, which means it's just like an integer variable. But what is the difference? What is the difference? The difference is that a equal to a plus 1 you can do directly, a equal to a plus 2 you can do directly. But in the semaphore you can't do such things directly, which means if it is semaphore S, then can you do S equal to S plus 1? No. Okay, these are the things not allowed. So what is the thing that is allowed in the semaphore? It is just like P of S and V of S. These are the two function calls are allowed. Other than that, nothing is allowed, and only the initialization you can do. Other than that, nothing is allowed. Okay, so what is this P and S? Let's just see what is this P and S, right? So semaphore support two operations, right? Semaphore support two operations. One is P, another one is V. Okay, P and V. So this P is also called as, some people call it wait. Okay, some people call it wait also. Some people call it down also. So basically, these are the different name of the same function. This V, some people call it signal. Some people call this down as up. Okay, so these are the different names for P and V. Is this okay to everyone? Just let me know. These are the different names for P and V, right? Okay. Now let's just see the type of the semaphores. So basically there are two types. One is the counting semaphore, another one is a binary semaphore. So binary semaphore is some semaphore which can take the value 0 or 1. Counting semaphore can take any integer value. So what do I mean by these semaphore? For example, if you do s equal to if you initialize it, okay, this is the initialization. Let's suppose if you initialize it to be 0 or maybe to be 1, and then you see it is a binary semaphore, then only the value possible for the binary semaphore is 0 and 1. Okay, 0 and 1 is the only possible value. Here you can have any integer value, right? You can have any integer value. Okay. Now let's just see the semaphore can be used. So semaphore can be, as I told you, that semaphore can be binary semaphore can be counting semaphore. Now you might be wondering that why we need, right, why we need two type of semaphores. Anyone who has already heard about semaphore, do you want to guess that why we need two type of semaphores? Okay, so there is one comment, sir. Someone said that there is an implementation of semaphore which show busy waiting is this true? We will see from the Galvin. Okay, don't worry. We will see from the standard resource that whether the busy waiting is there in the semaphore or this is not there. We will see from the standard resource. Don't worry. Okay. So now you just tell me that why we need two type of semaphores. One is counting, one is binary. Basically, generally we use this binary semaphore for mutual exclusion, right? You might have heard about mutual exclusion from last marathon. We will like tell you this mutual exclusion here also, but this binary semaphore is generally for mutual exclusion. This counting semaphore, okay, counting semaphore is generally to basically make sure that not more than, let's suppose if the value is 5 or value is n, okay, so we will say not more than 5 people can enter, right? So we will bound it, right? We will say for not more than 5 people can enter, something like this, right? 5 people can enter, okay, something like this. Okay, so I will tell you that what do I mean by not more than 5 people can enter and these things, right? Now let's just go to the next slide. So these are the two type of semaphore: binary semaphore and counting semaphore. Some people call it mutex semaphore also, but that's fine, right? So for example, that this counting semaphore can take any integer value. This can take only 0 and 1, right? Only 0 and 1. Okay. Now, what is a semaphore basically? Let's just try to understand, right? Let's just try to understand this. What is a semaphore? So this is just a layout that the semaphore is being implemented. Let me just tell you. See, as I told you, there are two functions, right? P and V. P and V. These are two functions using which we are going to access the semaphore. Now let's just see how we are going to access the semaphore using P, and what does P do? What does this B do? Right? Let's just see what does this P and V do. Okay. Sorry. Uh, if it is overlapping, then sorry about it. Okay. Now I hope that is fine, right? Okay. Okay. So let's just see what does this P do. What do you think this P might be doing? Let's suppose this is a binary semaphore, right? Binary semaphore, right? This is a binary semaphore. So what do you think this P might be doing? It will be like that. If we are executing this P, we are making sure that S is 0. Okay, we will say that S is 0. Okay, the moment we are executing this P, we will set S to be 0. The moment we are executing this V, we will make sure that S is 1. So basically this P is used to make this S 0. V is used to make this S as 1. Okay. Or in the counting semaphore, this is used for the decrement, this is used for the increment. So I will tell you the difference. See, if you talk about the counting semaphore here, instead of binary semaphore, let's just take it as a counting semaphore. Okay. So let's just take it as a counting semaphore. Here, this P will be used for the decrement, which means you can say S minus minus. Here it will be S plus plus, right? S plus plus. Okay. So this will be S minus minus. This will be S plus plus. Now, what else we need in this P? What else we need in this P? See, what we need in this P is basically that if someone with S equal to 0 is executing this P, okay, someone with S equal to 0 execute this P, then it should get blocked basically, okay? It should get blocked, right? If someone with S equal to 0 is making the call with P. Similarly, if someone with let's suppose whatever is the value, it will basically increment it, and let's suppose S value is initially -2 or something, right? It is basically -2 or something, because counting semaphore can take any value. Now it will increment it, and after incrementation also it is negative. Then it means that the process should not get through, which means basically you will be there is something called wake up. You will be waking up some other process. So let me just tell you the implementation from the Galvin, that what is happening. Okay, let me just quickly tell you the implementation from the Galvin, and then we will proceed with the examples. Okay, so see here, this is P and V. Okay, this is the implementation from Galvin. Okay. So here what we are doing in this p, we are decrementing it, and what we want actually, we want that if s is 0 initially, then we don't want to pass through this p, which means after decrementing, if it is negative, then what is, can anyone tell me what does this mean? Initial value cannot be more than 0. If after decrementing, if it is negative, then initial value may be 0, may be negative, right? So which means initial, if the initial value is 0, even 0 or negative, then I want to basically say that I want to basically put it in the queue. Okay, don't worry, you don't need to remember this, that what is the queue and all. We will make it very simple, but for now just understand that we are putting in the queue. Okay, we are putting p1 in the queue, and let's suppose if some other process is executing with the s equal to 0, then we will put that also in the queue. Okay, so we will put on the queue if some process with s value or 0 or negative is calling. Okay, then we will put in the queue. Now here first we are going to increment. Okay, and then after incrementing also, if it is less than or equal to 0, then we are sure that earlier it was negative, right? Earlier it must be negative, right? It must be negative. If after even incrementing, if that is less than or equal to 0, then earlier it is must be negative. So if someone with a negative value is calling, right, then this we will do what? This we will remove one of the process from the waiting queue. Okay, so don't worry about these things. Let me just tell you what this p and v in the simple terms. Okay, here you just consider this p as a decrement operation. You just consider this v as an increment operation, right? So basically whenever you are calling this p, then you will decrement the value. Whenever you are calling this v, then you are going to increment the value. For example, now if you are having, let's suppose if you are having s equal to 5 or s equal to 4. Okay, now you tell me after 2 call of p, what is the value of s? After 2 call of p, what is the value of s? S will be 4 here, right? S is 4 here. Now s is 3, now s is 2, isn't it? So after 2 values of p, the s is going to be 2, isn't it? Now if I ask you that s is initially 4 only, for example, and if I just ask you what's going to happen if you execute 1p and 2b. Okay, 1p and 2b. Can anyone tell me what is the value that it is going to come after 1p and 2b? See, after 1p it is going to be 3. After 1p it is going to be 3. Then it is going to be 4. Then it is going to be 5, isn't it? So at this moment the s is 5, right? S is 5. Is this okay to everyone? Now let's just take little interesting. Suppose it is a binary semaphore. Okay, suppose it is a binary semaphore. Then you tell me if you are having s equal to 0, then you tell me after, or maybe let's suppose s equal to 1. Okay, s equal to 1. After 2p, what is the value of s? What is the value of s you are going to get? What is the value of s that you are going to get after 2p? You are going to get s equal to 1 here. Here s will be 0. Interestingly, if it is a binary semaphore, then only 0 and 1 is possible. That's why s is 0 only here, right? S is 0 only. Is this okay to everyone? S is 0 only. Now let's just take more example. Now you tell me, suppose in the binary semaphore itself, okay, in the binary semaphore itself, you have two p's, right? P of s, v of s. Okay, two p's and two v's. Now you tell me what is going to come after this. Okay, at this moment, can you tell me what is going to come at this moment? See, s is 1 here, s will be 0 here, but in the binary semaphore, if s is 0, then you are not going to decrement it again. Okay, you will say s is 0 here only, s is 1 here. If it is 1, you are not going to increment again. It is either 0 or 1. Okay, so that's why it is s equal to 1 here only. Understood? Okay, understood. That's great, right? Now let's just understand the semaphore bit more. Okay, let's just understand the semaphore bit more. Let's see this question which has been asked in GATE 1992. What they are saying, at a particular time of computation, the value of the counting semaphore is 7 and 20. So they are saying the value of counting semaphore, right? So these are the counting semaphores that currently they are talking about, right? So the values of the counting semaphore is 7 and 20. P operations, this is only one semaphore, which is 7. Okay, there are 20 p operation and 15 v operation. So which means 7 minus 20 and plus 15, right? then what is the answer? It is going to be, 7 minus 5, which is 2, right? 2 is going to be the answer, right? 2 is going to be the answer. Easy question only, easy question only. This has been asked in ISRO also. Okay, so they have, the ISRO has copied this question. I don't know why can't they make even like this much easy question as an original question. Yeah, I know that ISRO has asked many good questions also, but they should at least stop copying, right? They should not copy, right? They should not copy. Okay. Now, this is 1998 question. What they're saying, that initially S value is 10 and then 6p and 4b. So 10 minus 6 plus 4. Then what does this mean? It means 10 minus 2. It means 8. So that's why B is the answer here, right? B is the answer. Yeah, this much easy question won't be asked most probably. But if they ask, then at least you should know. But yeah, this is not about the solving the question. It is about the understanding the concept. Once you understand the concept, then only you will be able to solve the critical questions also, right? Okay. Okay. So if you want, we can solve this particular question, which is really a good question. Let's just see what this question is saying. They're saying a shared variable. Okay, they just shared variable x that's initialized to 0. So there is a variable, right? There is a variable x which has been initialized to 0. And then what else they are saying? Let's just see. They're saying that there are 4 concurrent processes w, x, y, z, h follow h. Each of the process w and x read from the memory, increment 1 and store it to the memory. So they are saying that read from the memory. So w, x, y, z, these are the 4 processes, right? So they are saying they read from the memory, increment it and store from the store to the memory, right? Store into the memory. So these are the 3 steps that they do. So read, increment and store. Read, increment and store. Okay, so these are the 3 steps that everyone perform. That's what they are saying. Now they are saying that increment. Okay, each of the processes. Okay, w and x do these things, and y and z read, decrement by 2 and store. Okay, w and x is x, these two, and x and y and z basically, right? Y and z, they decrement 2. So instead of incrementing, what they do? So they read, they decrement 2. Let me write it as a, decrement 2 as a decrement underscore 2. Okay, so they decrement 2 and then they store it, right? Now what they're saying, each process before reading x invoke p on a counting semaphore s and invoke v operation on a counting. So they are saying that there's a p and v operations after storing x to memory. So basically they are saying each of the process is basically doing p here, let's suppose on s, and v here on the s. Okay, before read p and after store v. That's what they are saying. Okay, so let me write in all the processes p and v. Okay, now what they're saying, semaphore s is initialized to 2. What is the maximum possible value of x when the process is completed? Okay, so let's just see this. So they are saying that s is a semaphore, okay, which is a counting semaphore, and that has been initialized to 2. Now they are saying what is the maximum possible value, right? They are saying what is the maximum possible value of x. So tell me what is the maximum possible value of x which can be there. Now here you need to get the maximum, which means if it is possible, then you need to discard these decrement. Okay, let's just see. See, if the counting semaphore s is 2, then what does it signifies? That in a critical section, if you treat this as a critical section, then in a critical section, how many processes can be there at most? How many processes can be there at most? In the critical section, 2 processes can be there at most, right? Okay, so what you can do, maybe you can ask one of the process to hold on the value which is 0. Okay, you want the maximum, right? So what you can do, you can ask one of the process to hold on the value 0, You ask this process to finish, which means you can definitely get enter, and this process can definitely get finished, right? You ask this process to finish, you ask this process also to finish. So the sequence could be, you read this, okay, you just perform this, you ask this process to finish, you ask this process to finish. So both of them can be finished, right? Both of them can be finished, and then what you will do, you will say that, okay, since you have read 0, now you can increment it to 1, and then you can increment it to 2. Basically, you can definitely discard both of them, right? You can definitely discard both of them. So that is why the value of x, maximum value could be 2. Okay, so you can say the maximum value that is possible here is 2. Let me know if you have understood. Okay, so what you need to do, it is very simple. You just need to hold on that value, and then discard it. Discard means you execute it completely. Actually, if you execute it completely, then what is the value that you are going to store in the memory? If you execute this completely, you are going to store -2. Then you are going to store -4, right? -2 will get replaced by -4. But ultimately, since you have already read this 0, then ultimately what's going to happen? You are going to store this 1, right? This -4 will get replaced with 1. So that's the trick, that you can basically discard the final result of these two, right? You can definitely discard the final result of these two. Okay, I hope you understood this completely. Now tell me, what is the minimum value that is possible here? If I ask you the minimum value as a variation, okay, minimum value that is possible, minimum value of x, what is the minimum value that is possible here? Okay, so Govind Gupta is saying, "Sir, I'm facing issue in the paging and all." So see, Govind, I have already taken many sessions. Okay, I have already taken many sessions on the multi-level paging and these things. You just see this particular playlist. This playlist will definitely solve your doubt. Okay, so on the multi-level paging and these things, I have already taken session. It has got 18,000 views. Okay, you just check this playlist and it will definitely help you, right? Okay, so see this 18,000 views. Now you just tell me what is the minimum value possible. If I want to ask minimum value, then it is note to see that you should execute these two and you should discard these two. Can you discard these two? Yeah, you can definitely discard these two. How? You can say that, okay, let me hold on this value, which is x equal to 0, and then x will be, I mean, x is 1 and x is 2. You can make x as 1 and 2, and then you will say, okay, and then after this x is -2 actually, right? So after these two x is 2, after these two x is 2, but once you execute this, because you have already taken 0, then it will be -2. It will replace with the -2, and then -2 will get replaced with the -4, right? So that's how you can solve it, right? Now you tell me in the same question, if I just say, okay, in the same question, if I just say, so here it is a -4. How? You discard this, you hold it, and then it will be -4. But in the same question, if I ask, if s is 1, which means let's suppose they say it is a binary semaphore, or maybe s is 1, right? Maybe s is 1 directly. Then can you tell me? Okay, then can you tell me if s is 1? See, if s is 1, then you have to do systematically, which means you can't just hold and you can't just ask another process to get enter. So basically whatever is the systematic way, which means in whatever order you will do, it is +2, then -4. Okay, +2 -2, it will get cancelled out, then -2, right? So ultimately it will be -2 only. It is not minimum or maximum here. It will be -2 for sure. Okay, so here x will be -2 always, right? X is -2 always. Hope you have understood this, right? X is -2 always. Now let's just see more questions. Okay, let's just see more questions. Now let's see this particular question, which is really very interesting question, right? So let's see this question. So there are many questions which we are going to solve, right? So for example, let's just first see this question. Okay, what this question is saying, let's just try to understand. So they are saying, in this question they are saying, suppose the semaphore is initially 0. Okay, assume this is a binary semaphore. Generally, if it is 0 or 1, then it will be binary semaphore only. They may need binary. Even if you take a counting semaphore, doesn't matter. Okay, for this particular question. Okay, assume this is a binary semaphore which has been initialized to 0. Now there is a process A, there is a process B. These are the two processes that we have. Now if you have noticed, then they are saying that our goal is to execute. We want statement A2 in the process A to complete before the statement before. So they want this first and then they want this. Okay, so they want this to be the execution. Now can you tell me what is the, what is the possible settings that we can do such that we can make sure this? Okay, what is the possible setting that we need to do? See, if we want this and then this, then see, in general process B can come and process B can definitely execute before this particular statement, right? Before this A2, process B can definitely execute, but we want process B to wait here, right? We want process B to wait, which means it is definitely a good idea to put P operation here, isn't it? It is definitely a good idea to put P operation here, because what we want, whenever the process is coming to execute this particular statement, we don't want to execute it until and unless we have executed this A2, right? So here if you have noticed, there is an arrow. This arrow signifies the order, right? This arrow is basically to ensure the order in which we want to execute. Okay, so tell me, can I say that if I put the wait operation, or maybe P of s, since the s value is initialized to 0, then wanted wait, and I want this to execute after this A2, which means I can put V of s here, which means if A2 executed and this B of s is executed, then only it will get released, isn't it? So isn't it a very beautiful question, where either wait or signal, or you call it P or V, okay, doesn't matter, you call it P or V. So basically, isn't it a very beautiful question? If I want this before to execute it first, before to execute it after this A2, basically, right? So if I want if I want to wait on this before, then I can put the wait operation or the P operation here, and then I can make sure that after executing A2 only it will get executed. So the idea here is that with this problem you can understand one idea, right? You can understand one idea. Can anyone tell me why I'm showing you this problem? I'm showing you this problem for one purpose. And what is that purpose? The purpose is there that you understand that we can use this binary semaphore to ensure the order, right? So this is the application. You can understand this is the application of binary semaphore. To ensure certain order. Now let me just tell you there are many PYQs, okay, many PYQs on this application. We will see all the PYQs, don't worry, but I'm just telling you there are many PYQs on this application. Okay, so you just see here that what is happening, that what I'm saying here is that if you want to ensure that, okay, there's a process, let's suppose this particular statement P1, this particular statement should happen, and then only this particular statement of some other process should happen, then you can use the binary semaphore to make sure that this order is preserved. So here you will apply P, here you will apply V, right? Now tell me, suppose if someone asks you, okay, suppose P1 is there, someone asks you, let's suppose this P1 is having while 1, okay, there is a print statement, and let's suppose this is printing A, okay. Let me ask you a question. Let's suppose there is a print statement which is printing A, and there is a P2, okay. Suppose this is printing A and this is printing B. Now suppose what we want is that we want to make sure that whatever is the execution possible, we want to make sure that A should get printed and only then B should get printed, and after that only A should get printed, and after that B should get printed, and after that A should get printed. So we want to make sure this order is preserved. Okay, we want to make sure this order is preserved. Then can you tell me that what are the possible values of the semaphores? Maybe you can take two semaphore here, okay, s equal to 0, maybe t equal to 0. Let's suppose both are the binary semaphore. Then can you tell me P and V? How should I put P and V? See, I can say that okay, first A should be performed, right? Okay, maybe I can take one of the semaphore as one. See, I will tell you why. Okay, or maybe to start with, I can just have one of the semaphore only. Maybe let's suppose you just have only S. Okay. Now you tell me if you want this A to be get printed and then only B should get printed. So obviously this B should wait and this should be the case, right? Right? Isn't it? Isn't it? But you again want, okay, see that's very interesting problem, that here A will get printed and then we can get printed, that's okay, but here A can also get printed two times, right? A can also get printed two times. Is this really the desired case that A should get printed two times? No, right? You want to wait on this A also. So that's why you can put another semaphore, maybe T, right? T here. And then you can say that okay, after this B only this T will get executed. So initially the value of T could be 1 because you have to start with A. Now let's just see the flow. You will say that okay, this is the P value, this value will be 0. A will get printed and then you can't print this A again because this P won't allow you, right? Because this P of T won't allow you if T value is 0. So that's why you printed A and then you have to print B, right? Because this PS is allowed because you just did VS, so you have to print B, and then you can't print B twice, right? You can't print B twice. Why? Because if you want to print B twice, then what will happen? Then if you want to print B twice, then see this S value is already is like, I mean, you executed P, right? So you can't execute two P's in a row. Okay, you can't execute two P's in a row, right? So basically, if you try to execute this 2P, okay, on the same semaphore in a row, then it will be problem, right? You can't get it through. Understood? Let me know. Now let's just extend this problem. Let's suppose this is P1. Let's suppose this is P2. Let's suppose this is P3. Okay. Suppose you want, okay, here you are printing, let's suppose A. Here you are printing, let's suppose B. Here you are printing, let's suppose C. Okay. Then in that case, can you tell me that how many minimum number of semaphore needed to make sure that ABC will get printed? Okay. Let's suppose this is the while loop. Okay, this is the while one. Just tell me how many minimum number of binary semaphores are needed to make sure that you print A, then B, then C, then A, then B, and then C. Okay, then ABC, ABC, like in that way. Okay, how many minimum number of semaphores are needed? See, here you want to print A, right? Here you want to print A. So that's why, yes, this was the almost same question that we have that we have put in AMT4 also, right? That's true. In AMT4 also we have put almost same question. Yeah. You just tell me the C. If you want to print A first, right? And then B and then C, how many minimum number of semaphores will be needed? So you don't want to print this B and C, that's for sure. Then you want this P operations, right? You want P operations here. But obviously that is true for A also because you don't want to print this A arbitrarily, right? You are forcing the order. After C, you are forcing, but you are forcing the order. So since you are forcing the order, so that's why here also P, here also P, right? Okay. Now let's just see that what's going to happen. See, obviously if you want to print this A first, then that's for sure that whatever you want, right? I mean, let's suppose the semaphore value is S. So S must be initialized to 1, right? Because if you want to print this, then after that you can say this is, let's suppose, T, and then you have to put T here because you will say that okay, after this only you want to print this B, right? So T must be 0. T must be 0 because you don't want this to print arbitrarily. So T must be 0, and then you can print this B, and after that only you want to print it, right? After that only you want to print it. So maybe you can take another which is V of U, maybe, okay, or V of X, and this is X, right? And after C you want to print this S, so this will be V of S. I mean, you want to print this A. Okay. Okay, so basically you need three semaphores here. Okay, I will tell you why not only two or why not only one, right? See, you want to one thing is for sure, you want to have PPP here, right? And then VVV here, because after that you are enabling something. If you want to enable something, then there has to be this B, this has to be V, right? Now this S must be initialized to 1, right? This S must be initialized to 1, and then printf, and then you can execute this V, and see, then after that there will be the same semaphore, right? TNT. But can you again use S here? My question was that, can you again use S here or something? See, if you try to use, see, one thing is for sure, that this pair must be same, right? I mean, this is actually matching like this, right? The pair must be same. Okay. If you want to execute after you want to execute B, then this pair must be same. And now that's for sure clear that you can't have the same semaphore repeating. Why that is a problem? Then you want to be able to differentiate between A and C, right? Okay, you want to be able to differentiate between A and C. So that's why you can't do with only two semaphores. Okay, if you see, these are the 2 points that I want to convey. One is that if you're enabling, then this pair and this pair must be same, right? Okay, these pairs must be same. One thing is for sure. Another thing is that if let's suppose you are enabling B, right? Then if you are saying that, okay, here also I can use S, here also I can use S, then this is wrong. Why that is wrong? Because then you want to be able to make sure that A is printing first or C is printing first, right? Understood? Okay, great. So three semaphores are needed here. Yeah, you can use multiple combination of P and V in a single program. That's not an issue. Okay. Now, one thing you might have understood little bit, that semaphore. Okay, semaphore is used to ensure the order, right? Semaphore is used to ensure the order. Now let's just solve these kind of problems. Okay, let's just solve these kind of problems. Let me go over that problem. Yeah, let's just solve this problem which has been asking gate 2005. So this particular problem is basically based on the same idea that semaphore is used, okay, to ensure the order. Let's just see what they're saying. There are two processes, P1 and P2, and there are multiple resources, R1, R2, R3, R4. So P1 wants to use this, P2 wants to use this, but there is certain order that they have written. Actually, I've copied that order on the next page. So they are saying P2 must complete R1. Basically they are saying इसके R1 के बाद ये होना चाहिए. Okay, so basically, yeah, so they are saying, actually I have written on the next page, they are saying something like this. Okay, so first let me just copy it. Okay, what they are saying is something like this. Okay, so they are saying that this P2 must execute R1, and then you can execute from this P1, you can execute R1, right? And then they are saying P1 must complete the use of R2 before P2 get the R2. So basically they want to ensure this order. Then how many minimum number of semaphores are needed here? That's the question that they are asking. Can anyone tell me what is the answer? See, if you notice that they are saying that no scheduling constraint if the only binary semaphore is used to enforce the scheduling constraint. See, the binary semaphore is used to enforce the scheduling constraint, right? Okay. Now you just check here. If you want this kind of order, then can you say here I want to wait, right? Here if here I want to wait, then it must be P of S. It must be V of S, and S is initially 0 or 1. It must be 0, right? It must be 0. So basically it will make sure that this is happening. Let me know if that is okay to everyone or not, right? That should be okay. Now you just see here, you want to make sure this should happen, right? So which means you want to wait here, and then you want to basically enable it here, right? You want to enable it here. Is this okay? Now can you wait on the same semaphore as? Can you use the same semaphore? That is my question. Can you use the same semaphore? Will this enable the order that, okay, R2 के बाद ही ये होगा? Or maybe it may so happen that r1 can enable this, right? I mean, after this vs, you might not want to execute this. After this r1, you don't want to execute this r2, right? So that's why the same semaphore you can't use. See, you want to use the minimum number of semaphores, but it doesn't mean that you can use the same semaphore. I hope you can see the difficulty. What is the difficulty in using same semaphore? If you use the same semaphore, then obviously you are allowing it, right? So that's why you can't use the same semaphore. Maybe you can use t here, and you can say t is 0, isn't it? So if t is 0, then in that case you have to wait here. This will only enable. Now you tell me if you want to execute this order, okay, which means after this only this must happen. You must wait here, you must enable it here. Now you tell me, can you use s, maybe because it is too old. Can you use s? Can you use s? See, we cannot definitely use t, right? Because if we use t here, then that might be the problematic, because you can directly from this r2 can enable it, right? You can't use t, but can you use s? See, if you use s, will it be a problem, or it will be okay? Let's just check. See, if you use s, then what's going to happen? Then here, obviously, this can enable, this can enable. Can anyone else enable this? This also can enable, right? This also can enable. But we are already making sure that, I mean, see, we are already making sure that this order is already preserved, right? This order is already preserved. So basically, and this order is already preserved, right? We are already making sure that this order is already preserved. Till now we have already made sure this. Till now we have already made sure that this order is preserved. Let me know if that is okay to everyone. Now tell me, can this v enable? Which means, see, this v can enable, that's for sure. But can this b enable this? Obviously no. This b will get consumed, isn't it? This b will get consumed in this, right? This b will get consumed in this, isn't it? Because we have already made sure this. So this v doesn't exist anymore. I mean this exists, but what do I mean by doesn't exist anymore? Means the impact of this v is lost. Okay, someone must have already consumed it, because this order we have already made sure, this order we have already made sure. So this v is vanished, this v is vanished, right? So these we can't do anything, right? I mean, okay, so basically at least this we can't do anything, right? This we can't do anything, because this has been consumed by this p. Okay, this we have already made sure. So you can definitely use this s, and then you can definitely again make use of this t. Okay, so basically here, if you are waiting p of t, and this is v of t. So only two semaphores are needed. Only two semaphores are needed. This is really very nice problem, right? Because why you can use b of t, this p of t, because this v of t will only enable this, right? This v of t. Can this b of t enable it? Obviously no, right? Obviously no, because this must have been consumed with this, right? So only two semaphores are okay. Only two semaphores are okay. This is very good problem. So which has been asked in GATE 2005. So only two semaphores are okay, right? Now I hope you understood the application. See, the application part is very important. That many people don't understand this this particularly. They don't even know that this is application. Okay, so this ensuring the order is one of the very important application of this binary semaphore. Understood? Great. Now let's just solve other problems. Let's solve probably this problem. Let's see what this question is asking. This question has been asking GATE 2010. Let's see what this question is asking. They are saying the following program consists of three concurrent processes and three binary semaphores. Okay, so it consists three concurrent processes p0, p1, and p2, and three binary semaphores, where the values are initialized like this. Okay, now how many times p0 will print 0? So you first tell me, do you observe, okay, other than in p0, do you observe the while loop anywhere else? I mean, p0 definitely have the while loop, that I agree, but other than this p0, do you observe the while loop anywhere else? Which means this while one is only in p0, isn't it? This while one is only in P0, right? So basically you can easily notice here, this while true is only in P0. This will get executed but only once. Okay, wait and release, this is wait and release, this is wait and release, this will get executed, but these will get executed only once. Let's see what is happening with this P0. See, it will get executed again and again, right? It will get executed again and again. Okay, Vivek is saying, are these similar to locking protocols? Yeah, if you want to take a lock, yes. I mean, this is read lock. There you have read lock and write lock, but here we don't have the read and write concept. So in that sense, they are differing. But you can implement those locks using the semaphore. Okay, at the end you have to write the code. So here we are understanding that how to make sure that to write a code. So basically, once you understand those semaphore, you can implement those read and write locks, right? Read and write locks using these semaphores. You can definitely implement. In the DBMS, you have read and write locks, right? Okay. Now you see this S0 is 1, which means you can definitely execute this, right? And then you can print 0. And then you can release S1, then you can release S2. Okay, so here you have wait S1, you have wait S2. So basically you can't execute this P1 and P2 at first. So you must execute this and you have 0. Now you printed 0 once. You printed 0 once. Now you check. You have release S1. You have release S1, which means this particular value you can definitely make it to 1, right? You can definitely make it to be 1. And then you can definitely make this also to be 1. You can definitely after this release S2, you can definitely make both of them to be 1. Okay, I mean, I'm just telling you one possible execution. So let me just copy it. Okay, so basically one of the possible execution here is that you can make it 1, right? And then this wait of S1 will do what? This can make it 0. And the release of S0, this will be doing what? Since see, this wait of S0, you can't execute this twice, right? You can't execute this twice. So you just observe one thing. You can execute it once, and then if you want to execute it twice, then you have to release S0. Maybe from here, right? So you execute it. I mean, you print 0. Now, if you want to execute it twice, which means you want to basically execute it once more, then maybe what you can do, you can have this release. Okay, I mean, all of these, both of these will be 1, and then this will be 0, right? So after one time of this, you have printed 0. And these are the values that you have. Let me know if that is okay to everyone. After one time execution of this. Now, obviously, you can't twice execute it again and again. I mean, back to back, you can't do it. So, obviously, you have to make this release S0 via this or maybe via this. Now, let's suppose you make it via this or via this, doesn't matter. Actually, whatever you take it first, doesn't matter. So, you can take this. Maybe via P1, you release it. Okay. Which means you make this particular value as 1, and obviously, it will be 0, right? It will be 0. Now, this value will be 1. This value will be 1, and then you can print it again, right? Then you can print it again. So basically now you again do release. So maybe it will be again 1, and it is also again 1, right? I mean, it is already 1, basically, doesn't matter. Now can you execute it again? Yes, you can, since it is 1, so you can definitely execute it again. Sorry, this S0, it must be 0. It must be 0 after it, and then to execute it again, see the thing here is that this P1 and P2 are only ones, right? Are only ones. So basically once this P1 is executed, can you execute this P1 twice? Which means, can you execute this P1 twice? Then answer is no, right? Answer is no. So once this P1 is executed, you can't execute it twice. I mean, this is destroyed, which means it is not even in the memory, right? Once you execute it, you can't execute it twice. Similarly, once you execute this P2, you can't execute it twice. I mean, this is destroyed then, right? Okay. Now, see, in this kind of problem, you just observe one thing. You do this wait of S0. This will make what? this will make it a 0, right? This will make it a 0 initially, and then you print 0. Now you definitely have to release both of them, which means both of them is 1 now, right? Both of them is 1 now. Now the only thing is that if you want to execute this again, then either you execute this release or this release, right? Now see, I want to go here again, and for that I want this or this. Now the only thing is that if I destroy both of them, which means if I execute this and then this, then I'm losing one of the update to S0. Are you getting my point? So basically you can do one thing, you print 0 once, and this is the scenario. Then S1 can be 1, this S0 can be made 1 via this release or via this release. So what you do, after printing 0, you execute P1 and P2. Okay, which means this will be 1, and then again it will be 1, but it doesn't matter, right? And once you execute this P1 and P2, these are destroyed forever. Now you see here, you again want to execute it, which is okay. You print 0, you do whatever you want to do, but you can't do again, right? Because there is no one who can make you relieve, right? Who can help you. See, if this is release S0 and S1, so you will definitely print once, right? I mean, you will initially you will definitely print once. Now it will depend on you whether you are losing one of the update to S0, which means you are executing them back to back. If you are executing them back to back, then what is the problem? This release S0 will make this S0 to be 1. I mean, initially it is 0, then it is 1. Then this release, okay, don't worry about these weights. Okay, don't worry about these weights. Okay, don't worry about this, because it is just to make sure that once you execute this, then only you can execute this or this. Okay, whatever. So don't worry about these weights, just focus on this release. If you execute this release back to back, since it is a binary semaphore, it will be a problem. It will be one of the update will be lost. So you print 0 and then you execute them back to back. So which means only 2 times you will be able to print, right? If you execute them back to back. Let me know if that is understood to everyone. So you can print only 2 times. On what is the scenario here? You execute it and then you execute them back to back, and then you can at most 1 more time execute it, right? And not again. So only 2 times. But if you're little bit wise, okay, if you're little bit wise, then what you will do? Don't worry about these weights. These weights are just to make sure that you are executing this after this completion. Okay. Anyway, so if you're little bit wise, then what you will do? You will print one time. And anyway you have to release both of them. That's okay. Now you will print P1. I mean, you will not lose the update of F0. Okay. You will print you will execute this P1, and then you will print 0 again. Okay, now P1 is destroyed because this is not a while one, right? This is not a while one loop, so that's why it is destroyed. Now you can execute this P2. So basically you can even print 3 times or you can print 2 times. It depends whether you are doing P1 P2 back to back, or maybe you can say here you are taking the help of P1 and then you are taking the help of P2. Okay, then you can you can do something like this. So basically either 2 time or 3 time. So you can say at least twice. Yes, exactly twice. No, exactly is not the answer here, right? So exactly is not the answer. So that's why A is the answer. Okay, A is the answer. Understood? Easy question only. It's not a very hard question. Let me know if there is any difficulty in understanding this. Let me know. Okay. So basically, it's not a very tough question. It's just to make sure that you understand the semaphores. So basically, if you are having these 2 release, then you can lose one of the update. Okay, this is the one concept. If you don't want to lose, then it is beneficial. This is the one concept. Second concept here, you want to make sure that this, because of these weights, that you can say that after this only you will execute it, right? And the third thing is that there is no while one here. You need to see. You can't put the while one from your own choice. Okay, there is no while one here. While one is only in this P0. Okay. Now let's see this question which have been asked in GATE 1997. So what they are saying? each process, so they are having 9 processes like this, which are executing something like this, right? Which are executing something like this. And then there's a 10th process identical but v in place of p. Okay, so they are saying they have 10 processes. What is the largest value, that number of, what is the largest number of processes that can be there in the critical section at once? Okay, so generally, if they do not specify, then it is actually the binary semaphore. Okay, mutex generally means it is for the mutual exclusion, which actually mean the binary semaphore. So they are saying that there are 10 processes, right? There are 10 processes, and now in the 10 processes, it is like this, that all the processes have this P and V structure. For example, P1 to P2, everyone till P9, it is having P and V structure, but P10 is having V and V at both places. Okay, everyone is having P and V like this. Now you can definitely make sure that, okay, maybe P1 get entered, okay, or maybe P1 get entered, and then P2 can't enter, because if P1 is the critical section, then P2 can't go in directly, right? Then if P1 is in the critical section here, then P2 can't go directly, but this P10 can help, right? This is the infinite supply. Okay, repeat forever. This is the infinity supply of the V. Okay, infinite V, you can say. So basically, which means if you want to get help from V, if you want to execute V first, then no problem. You can schedule this, and then you can the P2 can be here. Similarly, P3 can be also here. P4 can be also here in the critical section, because whenever you need supply of V, there is a P10, right? And then whenever all the processes are here, then you say that, okay, P10 is also here. So what is the largest number of processes that can be in the critical section? Answer is 10, right? Answer is 10. This is an easy question only. Okay, answer is 10. Answer is D. So D here. Okay, answer is 10 actually. That's why the none is the answer. Understood? Great. Now let's just see more questions, and probably you will get to understand these things more, right? So see, all of these questions are based on only one thing, that ensuring the order, right? Ensuring the order. So in case of binary semaphore, this is very very useful. Binary semaphore is very very useful, because this ensures the order, right? This ensures the order. Now what they're saying, suppose you want to synchronize two processes P and Q using the binary semaphore S and T, and the processes are given below, right? Synchronization scheme can be inserted the point W, X, Y, and Z. Okay. Now what they're saying is that, which of the following will always lead to the output starting 0011001101? Okay, so they are saying they want to print this 00, then 11, then 00, then 11. So what should be the semaphore values, right? I mean, the semaphore has been, okay, you can initialize based on the option. Okay, S and T are the semaphore, right? Okay, so you want to print 00, then 11, then 00, then 11. One thing is for sure, that if you want to print 11 later on, there has to be P, right? This has to be P of something. I think this is easy question only, right? And this is also P, because in some sense you are also mentioning, but it can be initialized to be 1, right? Here S is 1 basically. Let's suppose T is 0, so T must be here, and then this must be V of S, this must be V of T, something like this, right? Let me know if that is okay to everyone. Understood? So basically you can say that it is, instead of W, it should be P. W should be P. W should be P. W should be, okay. W and Y should be P's. W and Y. Okay. Okay. They have given in all the options. They have given W and Y as P. Okay. That's cool. And then let's just check which of the following is a good option. So basically, with respect to W, it should be 1, right? I mean, if this is S, then, and with respect to Y, it should be 0. So I think, yeah, I think B is the answer, right? B is the answer. Okay, understood this? We have even solved this kind of questions, right? We have even solved this one, right? if A B A B, it is just instead of A they have printf 0, they have printf 0 two times, right? That's the only difference. But we have solved these kind of questions. I hope now you understood that these binary semaphores are there to enforce the order, right? So the ordering enforce is there in the binary semaphore. Binary semaphore is very useful to order the enforce, to enforce the order. So let me just tell you that how many questions they have asked using this particular, you can say, application, right? If you want to consider this also as a part of application, maybe, okay. And then this is one question they have asked, right? This is again second question, okay. So this is again the third question that we are going to see, okay. So yeah, so that, okay, just a second, what is the difference between that and that? Okay, this is basically another question, which is basically having another pattern. Okay, let's just check this. So what they're saying, which of the following will ensure the output string never contains the strings of the form 0 and, I mean, between two zeros there should not be even odd number of ones. So they are saying will ensure that string never contains this. So you don't want this, right? You don't want this. So let's just check. If you don't want this, then then what you need to do? Okay, let's just check this. So basically they are saying between two zeros you don't want odd number of ones. Odd number of ones means you first print it and then you go here, right? You first print it and then you go here. Is this even possible? You print this 0 and then you are saying you printed 0, this 0, then you print and then you don't want this odd, right? You don't want this one to print. Yeah, it is definitely possible. See, one thing is for sure here. If you're writing y and z here, right? If you're writing some entry and exit here, then if you can print this one, then there is no way to stop to follow. If you want, okay, if you want, then you can print this one also. See, it doesn't matter here, because if odd can't come, then how can even can come, right? You getting my point? See, it cannot be the case that between two zeros even can come and odd cannot come. How it can be the case? Right? See, if let's suppose somehow there is a code, okay, there is a code which is saying even can come. If even can come between two zeros, if you can print these two ones, then who is stopping you to print and then print only one? So if even can come, then odd can also come. If even can't come, then odd can also or also cannot come, right? Is this okay to everyone? Okay, so these are the two zeros, and between two zeros, if you are saying, if you're allowing even number of ones, then you're definitely allowing odd number of ones, and vice versa. If you're allowing odd number of ones, which means only one, then you're definitely allowing even number of ones. So basically they are saying odd number can't come. Actually they mean between two zeros, if you're having these two zeros, then any number of ones can't come. Okay, so here even and odd doesn't even matter. So basically they are saying between two zeros any number of ones can't come. Okay, any number of ones can't come. So what is the difference between previous problem and this problem? Here also they are saying 0 0 and then 1 1 can come. I mean between two zeros like this, then 0, okay, odd number of ones can't come. Okay, so this may so happen that this 0 0, and if you are having 1 1, yeah, so basically once you have this 0 0, right? I mean once you have this 0 0, then obviously you can have this 1 1, right? But can you just have just 1 1 and then 0 0 again? That is not possible. I mean that's what they are saying actually. Okay, so they are saying that, see, if you just have 1 0 and 1 0, in between any number of ones can't come, but if you have 2 zeros, something like this, then then you must allow. So basically, let me just tell you what they're saying is that if you have these two zeros, right? If you have these two zeros, and then these are the two zeros, so obviously between two zeros, then two ones can definitely come, but not only just, but one can't come. Okay, one can't come. So how to make sure this? How to make sure that cannot come and two one can come? So that's very easy, I think, right? See, if you see, one of the possible way is that if you use the same semaphore here, right? If you use P here, P of S, B of S, P of S, V of S, you make it atomic, right? You make it atomic. Then only 0, 0, and maybe 0, 0 again. But it won't be the case. It is atomic, which means it won't be the case that you after 0, 0, 1, 1 can be here and then you could print and then this 0, right? So basically, in between two zeros, all I mean, this is full and this is full. That's what you want, right? That's what you want. If you treat this is a critical section. If you treat this as a critical section, you want that one of the process should be here. This is completely executed, and then if you want, you can execute it again. No one is stopping you. You can print 0, 0 or two times. You can print three times. Doesn't matter, right? But if you're printing these two zeros, okay, then after that, if you're printing these two ones, then you have to execute this fully. Okay, you have to execute this fully. So I think only one semaphore is good enough here. So I think I think C could be the answer, right? C is the answer. So which means only one semaphore is good enough. This is just like a mutual exclusion problem. Okay, they twisted the word very carefully. So you just understand this. This is just like a mutual exclusion problem. Okay. So see here, they are saying that this 0, 0 you execute fully, and then you can't just have partial execution of this. Okay, the partial execution is not allowed, and then you do this. So basically they are saying one process is here, and then you can't execute this. Okay, so the partial execution is not allowed. This is just like a mutual exclusion problem. Okay, this is little tricky in the sense that they've twisted the words. Is this understood to everyone? Let me know. Okay, I hope this is understood, right? I hope this is understood. Now, okay, let me know by the way if there is any problem. See, what they are saying is that you execute this 0, 0 fully. Okay, and then you can't execute this also partially, which means 1, 0, and then 1, 1. Okay, something like this. Okay, you can't execute this 0 partially, neither you execute these ones partially. So basically the partial execution is not allowed. So that's what the question says, right? Very good question, I think, right? Very good question. The words that they have chosen to write this question is really nice. Okay, the only difference is in the words. Let's just solve this question. This question has been asked in GATE 2004. Let's just see what they're asking, right? Let's just see what they're asking. So they are saying, consider two processes P1 and P2 accessing the shared variable x and y protected by two binary semaphore Sx and Sy. Both are initialized to 1. P and V denote the usual semaphores where P decrements the semaphore value and V increments the semaphore value. Okay. So P and B are used, and Sx both are okay. Sx and Sy both are initialized to 1. In order to avoid deadlock, what are the correct operations? Okay, let me first tell you that how you can lead to deadlock. Okay, see deadlock in semaphore. Let's just see deadlock in semaphores. Suppose you have two processes, okay, P1 and P2. Suppose you have two processes P1 and P2, which is basically saying, let's suppose PS, or maybe you can have two semaphores, maybe let's suppose PS, PT, okay, and this is the critical section. This is, let's suppose, VS and VT. Similarly, here also you have the same thing, right? Suppose both are initialized to one. Both are initialized to one. Let's suppose that is the case. Now, can you tell me? Can you tell me? Is this possible to have the deadlock here? See, you execute this, and then you can execute this, or whenever you grab the lock, right? Whenever you execute it, can P2 execute anything? Can P2 even enter whenever you grab the lock? No, right? P2 can't enter. So there is no deadlock. I mean, deadlock is not possible here, right? No deadlock possible here. But interestingly, if you swap this, okay, if you swap this, which means which means if you do something like this, if you have T here and you have S here, let's suppose you have T here, you have S here. Now you tell me, in that case, can the deadlock be possible? Yes, this is possible, right? Why? Maybe you execute it, and then you print and then you execute it, right? You print and then you execute this, right? You print and then you execute it. So since you can basically execute it, and then you can preempt it, and then you can execute it, and then you can't execute this also, because P2 is holding the semaphore and P1 is holding S. That's why you can't execute this also. So that's why deadlock is possible here, right? If the order is like this is S and T and this is T and S, then deadlock is possible. Okay. Now you tell me, if you by chance, if you by chance, let's suppose, if you if you make this order reverse, okay, make this order reverse. This is S and T, this is T and S. Is deadlock possible here? But this order is same. Okay, this order is same. This order is same. Is deadlock possible? So here deadlock is not. See, if you change the order of V, if you change the order of V, then deadlock is not possible. Deadlock is not possible. Okay, if you change the order of V. So changing the order of V doesn't impact the deadlock, but changing the order of P impact the deadlock. Is this okay to everyone? Okay, let me know if you have understood this. Let me know. Have you understood? Okay, okay, great, great. So basically, if you're changing the order of P, then deadlock is not deadlock is possible. Okay, if you're changing the order of V, then deadlock is not possible. Okay, someone is asking, इसको spin lock भी बोल सकते हैं क्या? Spin lock means busy wait. So basically the semaphores doesn't have the busy wait. I will tell you. Okay, I will tell you how. Semaphores doesn't have spin lock or the busy wait. Cool. Now you tell me. Let's just solve this question. Let's just solve this question. Here they are saying that two semaphores are being used. Both are being initialized to one. And now, in order to avoid deadlock, the correct operators. Okay. So if you want to have the correct operators here, see, it is for sure that even if you see here, even if they have changed this order, okay, they have changed this order. If you notice, they have changed this order. Do you really think that you can make worried about it? You will be worried about it changing the order of V? No, changing the order of V actually doesn't really matter. But changing of this order will matter. So whatever the order is being followed, Y and X, then Y and X should be there. If X and Y is there, this is wrong, right? I mean, this can lead to deadlock. If this is X and Y, then Y and X, no. The X and X, okay, X and X definitely can lead to deadlock. This is X and X, Y and Y. Okay, I mean, once you execute this, it will always get stuck. Once you execute this, always get stuck, obviously. X and Y and X and Y, yes. So basically, D is the correct answer here, right? D is the correct answer here. Understood? So this is easy and nice question. I can say it's easy and nice question. So D is the correct answer here. Okay, understood. Cool. Now let's solve this particular question which has been asked in GATE 2013. Let's solve this particular question. This question is actually extremely nice question. Let's see this question. Okay, what they are trying to say. This is really a nice question. So you understood the order, right? I mean, the semaphores enforce the order, right? Semaphores ensures or enforce, right? Ordering. You can say ordering. Now suppose in this question, let me take this question example only. Suppose there is one array A. Okay, there is one array A. There is another array which is B. Suppose there is an array A, there is another array which is B. Now they are saying that, let's suppose there is a function or there is a process which is basically saying what, that f of I equal to a of I, which means this process is helping you, this process as x is helping you to fill these values. Let's suppose these are the n values, and then this process is running n times 0 to n minus 1, and this process is running n times and helping you to fill these values, which means a of I. First a of 0, then a of 1, then a of 2. Now this process y is helping you to fill the values of b, which means using a g function, some f and g are some functions, doesn't even matter to us, but using some function you are filling these values. Now interestingly, this b of I is actually some function of a of I, which means once you execute this, then only you are going to execute it. Okay, once this is filled, then only you can fill this. Once this is filled, then only you can fill these, right? So that's what they are saying. Okay, now let's just see further. What they are saying is that, okay, the structure of this, which of the following is correct implementation of entry and exit? Okay, so let's just move to the next page and let's just try to understand this. See, this is one of the question which got many upvotes, 89 upvotes, and I think in the answer also this is 132 upvotes. Okay, I mean, this is too many upvotes. Okay, so we must understand that what is the mystery behind this question, and why this question is so popular, right? Why this question is so popular, we need to understand this. Okay, let's suppose, let's not, this I is actually a private one, so I'm just removing it for the sake of having the space here. Okay, let's suppose we want the strict alternation, which means, suppose we want, okay, let's suppose there are two processes. Okay, p1 p2, p1 and p2. There are two processes. Let's suppose this p1 is basically doing one thing. It is, let's suppose it is printing, let's suppose it is while one, this is printing a. Okay, there is a while one, this is printing b. Okay, so there are let's suppose two processes, p1 and p2. This is printing a, this is printing b. Now suppose I want a b strict alternation. Suppose I want strict alternation a b, then we have seen that we can put p of let's suppose s, we can put p of t, this is v of t, this is v of s, and s can be initialized to 1 and t can be initialized to 0. So if you do so, then this is a strict alternation, isn't it? So this is strict alternation. Okay, which means a b and then b a b like this, right? Now don't you want the same thing here? See, here in this particular example, what do you really want is something like this. This is a, this is b, these are the n cells here, these are the n cells here. What you really want is basically, maybe you fill this and then strictly you fill this, and then probably you fill this, then you fill this, you fill this, then you fill this, isn't it? If that is the, if you fill this, then you can definitely fill this. So basically, suppose if I'm free to execute in whatever way I want to, I want to write the code. Okay, if someone give me the liberty to write the code instead of forcing me to write the entry and exit and these things, right? So if someone give me the liberty, then I will say, see, I will say, let me write p of p of, let's suppose s, and then this is v of t, this is p of t, this is v of s, and probably I can say s is 1 and t 0, isn't it? I can solve this problem very easily if I have liberty to write p and v in my own way, right? In the way that I want. But the question is not that straightforward. So here see, one thing is there, that we have understood, that they want us to implement this entry and exit. And what are these entry and exit? These are some combination of these are some p and v. Okay, p and v. So basically they are saying you need to, you see, I am saying that I can write p here and v here, p here and v here, right? I can enclose, right? I can enclose. But they are saying you need to write, not at the enclosure, not at this and this place. You need to write whatever you are writing, okay, in this particular code, whatever you are writing, you write at this place only. Okay, whatever you are writing, you write at this place only. See, if someone give me the liberty to write at this place and this place, this place and this place, maybe one before, one after, one before, one after, I will be very happy and I can solve this problem very easily. Let me know if that is okay to everyone, that you can definitely solve this problem if someone give you the liberty to write PV, right? Because that is a strict alternation, then, and you can definitely make sure that strict alternation is followed. But now they are not saying that that you can do of your choice. They are saying you want to insert p and v, you insert at the place that I am asking for, not at the place that you want it. So they want to insert this p and v here. Okay, so one thing is for sure, that if I want this and then this, right, then maybe I want v of s here, or maybe v of something, right? S or t, actually it won't matter, but let me just check that in what way they have written. Okay, maybe they have used r and s. Okay, they have used r and s. So maybe I can say I want v of r here, and then if I have v of r here, then I can say I will be executing it. Okay, I will be executing it, and then if v of r is here, that I will be executing it, and then maybe here at this place, in this entry, I can have p of r, isn't it? So see, once I execute this v of r, and then only I will be able to execute it, isn't it? Can I execute it twice? Can I execute this b of r twice? P of r twice? Can I execute this p of r twice? Tell me. Answer is big no, right? Because this is p of r. But interestingly, can I execute this b of r twice? Can I execute this b of r twice? Answer is yes. Answer is yes, because b I can definitely execute it twice. So that's okay. I mean, see, will there be any problem even if I execute it twice? No, right? As per the question, this is not dependent on anyone. Okay, I mean, strict alternation was just one example to tell you, but as per the question, this is a of I. This is not dependent on anyone. So it looks like this simplistic code is fine, which means I can write b of r here, I can write p of r here. I'm making sure that I don't execute it without executing this, right? I'm making sure this, and obviously I can execute it any number of times if I want to, right? If I want to, I can execute any number of times. So it seems like that this simplistic code is serving me the purpose of entry and exit. But here is a catch. Can you think about that catch? Okay, just think about that catch. See, the catch here is that this is very interesting catch. Tell me, do you have infinite supply of this loop, or after some point in time this process will get vanished? Tell me, isn't it the case that after some point in time this process will get vanished? I mean, after n times loop execution, this process will get vanished. So if you execute it again and again, then it's not a good idea. The reason being is that, let's suppose this process is vanished, then who will supply v to this p? You will only you say that, okay, let me fill all of this. Then the moment you try to fill all of this b, you can only fill once, isn't it? Because you can't have infinite supply of this v. Okay, this is not a while one loop. Understand this. This is not a while one loop. Hence you can't just have infinite supply of this. So that's why it seems like a strict alternation even is actually a better idea. Because in fact, if you do it twice, okay, if you do it twice, then also it is a problem. Basically, I want for every v, I want this p to get executed. I don't want any update to v get lost. Okay, so here is the idea that we don't want any update of v of r to get lost. This is very important idea. Let me know if that is okay to everyone. Is this fine? Okay. So I hope that is fine, right? So basically, I don't want to execute it even twice, right? Because for every v, I want this p to get enabled. So hence, this simplistic idea might not work. I need to do some more modification. This is okay. This is what we need. But we need to make sure this also, that after this p, okay, or maybe you can say after this b, I don't want to execute it again. So basically, since I don't want this v to get executed two times, right? I don't want this v to get executed two times. So I need to write a p here, or maybe p here. So you just tell me where I need to write the p. Here it is better, or here it is better. Okay, just tell me up it is right, some p is better, or down some, or maybe at the, you can say, uh, okay, top or bottom or whatever. Okay, at one place, at the place number 1 or place number 2, at which place writing p is better. If I want to make sure that I don't want even this v to execute twice, I want the strict ordering. I want this b, and then I want this p only. I don't want to execute this b twice. If I execute this twice, which means if I fill these two, okay, I mean, filling these two is okay, but I don't want to execute this twice. Because if I execute it twice, then actually I'm basically saying that only one time I'm enabling this p, which is not a good idea. So since I don't want to execute it twice, so that's why I need to put a p on the top. Okay, so let's suppose p of s. Is this okay to everyone? I want to put p on the top, which is p of s. I mean, the way the semaphores are being used, they are using r and s. Okay, so p of s. Now obviously I want to enable here. I want to enable this here. So here I have choice of writing v here or v here. So where I should be writing v? At place number 1 or place number 2? I want to write v of s. Where I should be writing? Just think about it. So see, what I want, मैं चाहता हूँ ये हो जाए, उसके बाद ये आए, right? And also I don't want to, similarly I don't want to execute that v also twice, right? Whatever that v is. Okay, that's ultimately interesting problem. Okay, so I don't want that. I want to write this v, but I don't want to lose update on the v also. So what is the answer? Just let me know. This is really one of the very good question. Okay, one of the extremely good question, I think I can say. So what is the answer that you people are getting? See, I want to write one of the V, right? Should I be writing it here or should I be writing it here? Let's just see. Let's just see. See, I want this V of R, and then I want to execute this, right? I mean, I want that. I see. We started with the idea that once I execute one of this, then I should be executing this. So this V of R and P of R was okay, and then I don't want this V of R to execute twice. Then that's why I protected with P of S, and then there should be V of S, right? Here or here. So this S being initialized to 1 and R being initialized to 0. Sorry. Uh this S I okay. This is V of R. Yeah, I think let me just check the initial values do they have. Okay, both are being initialized to 0. Okay. Sorry, both of them are being initialized to 0. That's the catch. Okay. So that's for sure. If both of them are being initialized to 0, then you have to write it at place number 2, right? If both of them are initialized to 0. So B of S must be here, right? So PS, VR and PR and VS. So PS, VR, PS, VR and VS and PR. VS and PR. So it must be at place number 1. If it is place number 2, then obviously the P and P. Sorry, I just I mean that was a slip of tongue. So basically, I'm saying it must be at place number 1 only, right? It must be at the place number 1, because if it is a place number 2, then P and P both will be get stuck, right? So basically, it is PS VR and then VSPR. VSPR. Okay. So C is the answer here. Let me just do this question once again, because that might be a bit tricky for you guys. Okay. To be honest, it was one of the very tricky questions. So let's just do it once again. See, let me remove this. See, what we want is that there is no infinite supply of this. There is no infinite supply of this. What we want to have the strict alternation kind of thing, and both of R and S are being initialized to 0. Okay, it is given in the question. Okay, that R and S are being initialized to 0. Okay, it is given in the question. Now let's say that I want to execute this, and then only I want to execute this. This is one very minimal requirement. So that's why I said there should be V of let's suppose R, and this should be some P of R here, right? This is one minimal requirement. Okay, or maybe if you want, I can make some space and I can write all the things here. So basically, I am saying this is B of R, this is P of, this is B of R, this is P of R, right? Okay. So what is happening here? That I am saying that okay, you execute it, and then only you can execute it. But the only problem is that I can execute it multiple times, and I don't want to execute it multiple times. And why that is the case? Why that is the case? Why I don't want to execute it multiple times? Because there is no infinite supply of this. So if you execute it multiple times, which means you are filling it, then the only problem is that who will supply once this has got destroyed, who will supply the this V to this process Y, right? So that's why you want to make sure that you don't execute it twice. So that's why you are having P of S. Okay, I mean P, R and S both are initialized to 0. You are having P of S here. Now there must be corresponding B either here or here. So where it should be? Where it should be? Obviously both are initialized to 0. You can't have this B of S here, otherwise it will be a problem. This is P of S, P of R. So that's why this B of S must be here. Okay. So PSVR and VSPR. So this is the answer, which is C. Okay, this is one of the very difficult question. If you understood, then I will be very happy. So C is the answer, and this is really a very good question. That's why this question has got 132 of votes. I hope you understood it very logically that what is happening. See, generally people do not even understand that okay, this is n. Okay, this is not an infinite supply. This is not an infinite supply. So Abhirap is saying that if the spin lock, if it is not provided, should we use a queue or something? Yeah, semaphore. In the semaphore, you always by default. I mean, I have not even seen in any book, so that's why I think in the semaphore you don't even say that it has, it doesn't have the queue. Semaphore always have the queue. Okay, semaphore always have sleep and wake queue. Okay. Even in the Galvin, there is a chapter called semaphore implementation. Whenever they talk about semaphore implementation, they have told that the queue is there. Okay, Abrup. So Abrup was asking this doubt, so that's why I have taken this doubt. Okay. Now let's just see one of the very nice thing, which is which is something that I have waited for. And what I'm going to ask you is basically something which most of the aspirants won't be able to answer. So my question is that we have seen the semaphore and we have said it that okay, there is a decrement operation, there is an increment operation here. But don't you think that this decrement and increment itself is a race condition? I mean, multiple processes can execute this wait, and multiple processes can execute this signal. See, this P and B operations are where these are in the operating system. This is because we are taking the support from operating systems. But operating system is not a black magic. It is also a code, right? Also just a code. So if you're writing in the operating system itself, if you're writing this s minus minus and s plus plus, don't you think that you again have the race condition? So which means that okay. So which means that we wanted to solve the problem of race condition, and then we said that okay, we can use the semaphores, but the semaphore itself seems to be having the race condition, isn't it? So how to solve this problem? So maybe you can say that some of the people might maybe they can say that we can use a test and set. Okay, before s minus minus we can use the test and set, which means if multiple processes are executing it, then they will get stuck here, right? They will get stuck in the test and set, isn't it? See, my question is that how to make it atomic, right? Making the operation atomic. How to make this P atomic? Maybe you can say that okay, if you want if you don't want multiple processes, maybe you can have test and set here. You can have block equal to 0 here. But do you remember what is the problem with the test and set? Because it is a spin, right? It will be waiting in the loop. It is a busy wait, right? It is a busy wait. It is a waiting in this loop. So to solve this problem that it is waiting in the loop, we said that we can have the semaphores. But if in the semaphore itself we are writing this loop, then what is the point, right? How the semaphores are better than just test and set? Okay, see, this is the semaphore. If in the semaphore itself I am writing the test and set to make this atomic, then how the semaphore is better than the test and set? This is my question. Okay, I will give you 2 minutes to think about it because this is very important. Okay, just think about it. This is very very important that how the semaphore is different from test and set. Let me tell you one thing that in the real implementation, this is true. The semaphore have the test and set. Okay, semaphore have the test and set. So whatever is shown in the screen is actually written in your Linux. It is written in your real operating systems. But how then how it is better than the test and set? This is my question. Just take 2 minutes and answer this because most of the experience won't be able to answer. Just answer this. Just think about it. Okay, so you might have thought about it. So let me just tell you that how the semaphores are better than test and set, right? So see here that you have test and set. So what was the problem with the test and set? Let's suppose let's suppose you don't have the semaphore. I mean, this is just a usual test and set. So what is the problem with this test and set? Okay, don't worry about the semaphore. Let's suppose you don't even know the semaphore. So you will test it. If it is already one, you will be waiting, right? The process will be waiting in this while loop, right? You will be waiting in this while loop if this is already one. And then other process. So basically, there are two processes. Let's suppose P1 and P2. One of the process is in the critical section, and another process is executing this while right. So which means one of the process in the critical section, another process is stuck here. Okay, P2 is stuck here, stuck, and it is executing, right. And then whenever it gets a chance, it gets stuck because it is executing. Whenever it gets a chance, P2. Let's suppose whenever P2 is getting a chance, it is in the loop because P1 is in the critical section. So what do you think that P1 is in the critical section for how long? It may be for a long time, right? Okay. I mean, there's a problem of busy wait. Okay, there's a problem of busy wait. Now, I'm sure that most of the aspirants won't be able to answer that how the semaphores is being implemented. Even if let's suppose rare people can answer that, okay, we can implement it using test and set. I mean, people should first of all be wonder that, see, we wanted to solve race condition, and this is also having the race condition, right? So how to solve this race condition? Okay, using test and set, let's suppose. Okay, but this test and set earlier was having the problem of busy wait, right? But now, don't you think that it is also again? I mean, we are recreating the same problem. The answer is no. Okay, I will tell you with the Galvin that in the Galvin what is written, but before that, let me just tell the answer here. The answer is no. Answer is a big no. That we are not reinventing the wheel. Okay, we are not reinventing the wheel. See, what is happening here is that you will execute this. I mean, let's suppose this is P1, this is P2. P1 is executing this, right? And P2 also want to execute it. So what will happen? P1 will go here, and it will say that, okay, initially log is 0. So P1 can execute this. Now you tell me how many lines of code this is. Isn't it a fixed line of code? Maybe 3, 4, 5, 10, or whatever, right? So it is a very, very short code, right? Very short code, isn't it? It is a very short code. Hence, if P2 is waiting here, then how long? Whenever P1 gets scheduled, it will get scheduled in just one quanta. Okay, in just one round robin, it will say that, okay, my lock is now 0. So see, earlier this critical section could be arbitrarily long. This is a user's critical section, right? User can write any long, okay, any long critical section. This is what user can write, okay, any long critical section. But here, if you treat this as a critical section, then this is a fixed, this is a very short code. So that's why P1 even is in the critical section, then it will not be more than few milliseconds. That's why P2 would not be waiting forever. Okay, I mean forever in the sense will not be waiting too much. And that is what written in the Galvin also. In the Galvin, you can see at the page number 217. Okay, at the page number 217, you can see that they have written very clearly. Let me just read it for you. They have said, that it is important to admit that we have not completely eliminated busy waiting. See, we have not completely eliminated busy waiting. Okay, that's for sure that we have not completely eliminated busy waiting. With the definition of wait and signal operation, rather we have moved the busy waiting from entry section to the critical sections of the application program. Further, we have limited busy waiting to the critical section of wait and signal operation, and these sections are short. If properly coded, this should not be more than 10 instructions. Okay, so the critical section which we are talking about currently is basically very, very short. Okay, so thus the critical section is almost never occupied and busy wait occurs rarely. Okay, and that too for a very short period of time. So they are saying in the semaphore, this is a Galvin. Okay, this is Galvin. So they are saying in the semaphores, this is basically like, I mean, if you consider this as a critical section, then this is a very short code. So that's why if P2 get stuck here, then how long? Very short time. But if it is a arbitrarily critical section, if test and set is basically within the, I mean, for protecting a arbitrarily critical section, then it is definitely the problem. Understood? Okay. Like, I hope you understood that we are not reinventing the wheel, right? So it's a vigibate again. So answer is no, right? No. How semaphores are better than just test and set? It is better. It is better because test and set are enclosed in arbitrary critical section. Here the critical section in which the semaphore the test and set are being used is basically for a well defined just 10 instructions. That's what the Galvin says, right? Now can you answer the question, that the first question is that, can you answer the first question, which is that, if the semaphore, if the semaphore is just like this, if the semaphore is also doing the decrement, then who is taking care of this race condition? Who is taking care of this race condition? Can you tell me? Test and set, right? Who is taking care of race condition here? Test and set, right? So test and set is taking care of this race condition. This is the first thing, that test and set is taking care of the race condition. Now the second thing that we want to convey is that if you use the test and set in the arbitrary critical section, then it can take any long time. But if you're using this test and set in just well defined very short code, then it is just 10 instructions. Okay, tell me if that is okay to everyone, right? So that is the difference. See, this test and set, if we are using for any arbitrarily critical section, then it's a real vigibate problem. But here if you're using only for the semaphore, it's not a vigibate problem, and that's what the Galvin also says. Okay, that's what the Galvin also says. Understood? Cool. Let me know if there is any doubt here. Okay, great. So we will talk about this classical synchronization problems now. Do you want me to talk in this session, or we can take just 2 hour long session, one more 2 hour session for this classical synchronization problems? This is actually a very good topic, and there has been many questions from this classical synchronization problem. For example, one question, two question, three question, right? Four questions, five, six, okay, six, seven. I think almost 10 questions I have here currently with me, right? From the PYQs, I'm saying from the PYQs, 8, 9, and from the writing philosopher also 1 or 2 questions. So 10 or 11 questions from the PYQs itself I have in my current slide. Okay, that's what make this particular topic very interesting. And actually, it is interesting. Some of the people find it very boring. Okay, some of the people find it very boring, but it's really a very nice topic. Okay, great. So let's just do one thing. We will start this classic synchronization problems in another session. Okay, we will start this classic synchronization problem in the another session, right? Cool. Hope you really understood what most of the aspirants doesn't even bother. Okay, because in the gate they can definitely ask that who is implementing this race condition, right? I mean, who is implementing this race condition. Test and set is being used, but this test and set, if I just ask you, okay, this is actually the university question only. I will put the link. If you ask me in the comment, just ask me in the comment, and I will put you the link. This is a university question only. Okay, that that semaphore completely avoid busy wait, completely avoid busy wait. Tell me, is this true or false? This is actually false. It doesn't completely avoid in the sense that there is just very short busy waiting. Okay, the busy waiting is just for this short period of time. There's a very short busy waiting, right? So hence it is false actually, right? False. There's a very short busy waiting. Okay, cool. So Thank you, everyone. I will just ask me in the comment for this particular true and false. I will put that link for the standard university link in the comment. Okay. Just ask me if you want to. Okay. So thank you, everyone. We will take one more session to make sure that you understand this classical synchronization problems very nicely, because this topic is also very interesting. Okay. Great. Thank you. Take care. Bye bye. Okay, just one thing. Just before I go, just one request I would like to make, that if you have really liked, okay, the kind of explanation, if you're really liking that, okay, we are going in depth to make sure you understand everything crystal clear, then just put us a comment. Okay, just a little favor that we want is just put us a comment and let us know how much you like the session. Okay, your one comment will motivate us a lot. So just put us a comment and let us know how much you like. Okay. Okay, just put us a comment later on. So how many of you can do it? I hope most of you can do it, right? Just let us know. Just one word comment is enough. You can say loved it. You can say whatever you want, right? Just one word comment is even enough. Just put a comment. Okay, so that we really stand out. Okay, we really stand out among others, because we are going really in depth, truly in depth, to make sure that you understand everything very clearly, right? Okay. Thank you, everyone. Take care.